regression analysis. Basically, in this session, we will try to estimate a relationship between two variables, if there's any. So, for example, solar radiation depends on sunshine hours, and air quality in a reservoir is actually dependent on the pH value of the water. And also there's a correlation between speed, depth of cut, and tool angle with the surface roughness of a metal being cut. These are some examples where there could be a relationship between exist between a dependent variable and one or more independent variables. Right. So the response variable, or the output what we measure, is usually denoted using the letter Y, and this is the response variable or the dependent variable. The independent variables are the predictor variables. We denote it using X, and if there are more than one such variables, we use X1, X2, X3, so on and so forth. If we can come up with an equation that relates all these X's to Y, then we call that as a regression equation. Actually, we are interested in determining the exact form of the relationship that exists between these variables. If it is possible, we try our best to express that relationship using a mathematical equation, which we call as regression equation. So these equations could be, for example, y is equal to 2 plus 3x, or it could be something like y is equal to 3 plus 2x plus 5x squared. And if there are more than one x variable, it could be the relationship could be expressed using y is equal to 3 plus 7x1 plus 5x2 plus 4x3, and the list actually goes on. So these are known as regression equations. Before we come up with equations, we should know whether there is a relationship exists between the variables, right? So the best would be to plot them and see if there is a relationship. So whether you can visualize a relationship after plotting the data, right? So let's assume that we have only one variable, and you can see there are three plots. So the first one, you can see that almost all the data are aligned to towards a diagonal, and when x increases, y also increases. If you can find such variations, we say that there is a strong positive linear relationship. If you move to the second figure, there also you can see the points are congested in a particular way, and in contrast to the first one, when x increases in the second figure, y actually decreases. That is also a relationship, right? So it is a strong negative relation because it happens to all the points that we have plotted. Okay, so we call it a strong negative, again a linear relationship, right? A third one, you cannot see an obvious pattern in the data, so we say that there's no relationship visible. Okay, if we have two variables x and y, we can use Pearson correlation coefficient to find out whether there is a correlation. Okay, so this coefficient is denoted using rho or tau. So rho is defined as covariance of x and y divided by the square root of variance of x, the square root of variance of y. So the covariance x comma y, you can write it as the expected value of x minus x bar into y minus y bar. The variance of x is expected value of x minus x bar whole thing squared, and similarly variance of y is equal to expected value of OE of y minus y bar whole thing squared. So this rho value is a number between -1 and +1. So the first figure, you can see rows being more or less equal to 1. The second one more or less equal to -1, and third one is more or less equal to 0. Right. So depending on how you have visualized the data, you can actually assume models for the behavior of the data. For example, if you can observe a linear relationship, we can denote the relationship using a linear model. For example, y is equal to beta naught plus beta 1x plus epsilon. So here the beta naught is the intercept of the y-axis, beta 1 is the angle, and epsilon is the error or the residual. Okay, so, and if you look at the second one, it's a quadratic model, and the model is y is equal to beta naught plus beta 1x plus beta 2x squared plus epsilon. And third one is a cubic model, where the equation is y is equal to beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed plus epsilon. Here is an example. A solid is removed from a material, which is y, is thought to be related to the drying time, which is x. So 10 such observations are taken from an experiment study, which is given below. So you can see the dependent variable values and the independent variable values, and if you plot them, and if you can find its Pearson correlation, and you can see visually there should be a positive linear relationship, because the points or the data points are linearly showing a relationship towards its diagonal. So you should expect a value actually closer to 1, and you can see actually rho is equal to 0.845, which is kind of a strong linear relationship. And a second example, an electric power consumed each month by a chemical plant is thought to be related to the average ambient temperature x1, the number of days in the month x2, and the average product purity x3. So the past year's historical data are available and are presented in the following table. Right, and you can see the y values and the associated independent variable values x1, x2, and x3. And for these data, the regression model could be written as y is equal to beta naught plus beta 1x1 plus beta 2x2 plus beta 3x3 plus epsilon. Okay, so what the things that you have discussed regarding the regression models, we can actually divide them into two main types of models. The first one is linear models, the other one is non-linear models. And if you look at the linear models, you can easily see that there are two variations. So the first one is simple linear models, And secondly, it is the multiple linear model. So in the multiple linear model, there are more than one independent variable. You can see in the simple linear model how the model looks like. It is y is equal to beta naught plus beta 1x plus epsilon. And for the multiple linear models, it could be one of them, y is equal to beta naught plus beta 1x plus beta 2x squared, or it could be y is equal to beta naught plus beta 1x plus beta 2x1 x2 plus beta 2x2 squared, or it could be something like y is equal to beta naught plus beta 1x1 plus beta 2x2 plus beta kxk, etc. and etc. And there are more in the list. If you look at non-linear models, there are intrinsically linear models, which means that you can actually transform the model into a linear model, and there are non-intrinsically linear models where you cannot find a transformation to make it a linear model. Now, for example, if you take y is equal to e to the power beta naught plus beta 1 x1 squared plus epsilon, if you take the logarithm of both sides, it is ln y is equal to beta naught plus beta 1 x1 squared plus epsilon. So that is a linear relationship. So that is intrinsically linear model. And if you take y is equal to e to the power beta x epsilon, so that becomes, if you take the logarithm of both sides, ln y is equal to ln beta plus ln x plus epsilon. So that is again a linear model. But if you look at the non-intrinsical model, it's very difficult to find a transformation to make it linear. So these are the models that are available for us to study, and we will focus mainly on the first three of them, which is the simple linear model, multiple linear, and the intrinsically linear models. Okay, so the first one is simple linear regression. So the simple comes from because we are using only one independent variable, okay, and the linear comes from we are observing a linear relationship. So so that is the simple form of regression model that we are learning. So regression model looks like y is equal to beta naught plus beta 1x plus epsilon. So the epsilon is, as I told you earlier, is a random error, random noise, or sometimes we know it denoted as a residual. In this figure you can easily see what I meant by the residual error. In this figure, certain points are actually lies in the line itself, but certain points are actually located a little bit away from the points. So the vertical distance from the line to the point is the actual actually I'm looking at, which is the residual or the epsilon. Okay, so there could be epsilon 1, epsilon 2, epsilon 3, so on and so forth. So remember, epsilon is nothing but the vertical distance from the line, the best fitted line, to the point that you are looking at. Okay, now suppose we have a variable, sets of variables x1, y1, x2, y2, and xn, yn. Then the model could be written as yi is equal to beta naught plus beta 1x I plus epsilon I, where I goes from 1 to n. So if you substitute x1, y1, it will be y1 is equal to beta naught plus beta 1 plus x1 plus epsilon 1. And if you substitute x2, y2, it will be y2 is equal to beta naught plus beta 1 x2 is equal to epsilon 2. Right. So when you have such points, you can actually draw many points that would fit the data. that would fit the data. But there